Jun2007 qu2. A body may be in equilibrium under the action of a number of coplanar forces and torques. A torque is a turning effect of a force. Define the moment of a force. Illustrate your answer with a labelled sketch. And so we're going to just draw some kind of lever. And we're going to label at the end a force. We're going to have a pivot. And we're going to have a distance and a right angle. And so therefore we're going to say that torque is equal to the force multiplied by the perpendicular distance from the force to the pivot. Or you could say the torque about a point, and then from F about the point would be fine. And the rest of the question is all about equilibrium. You can answer the second bit. The rest of it you don't need to know. So one of the conditions for the body to be in equilibrium is that the vector sum of the torques, i.e. the turning effects or moments acting on the body, is 0. State this condition in terms of moments. So at equilibrium is the first bit, and then the sum of the clockwise moments. I'd write the whole word out there, I just haven't got room. You write the whole word out there, should I say. The sum of the clockwise moments about a point is equal to the sum of the anti-clockwise moments about the same point. And you don't need to worry about the rest of the question there. In fact, you can actually do the question on the next page, so I'm just going to go through it anyway. A patient with one leg in a plaster cast is required to lie with the leg supported in a horizontal position. A nurse arranges a sling, a pulley system and a suspended mast to provide the support as shown in figure 2.1. The system is in equilibrium. The leg in its cast, which can be treated as rigid, can be assumed to pivot about the hip joint here. The rest of the patient's body lies horizontal on the bed. The centre of gravity G of the leg and cast is at a point 0.36 metres from the hip. The mass of the leg in the cast is 15 kilograms, so I'm just going to put that in here. And it's going to be 15 times 9.81 is its weight or force. Okay. Use equilibrium condition you stated in A part 2. Now A part 2 is your clockwise moments and anti-clockwise. So this is why I'm going to do this, even though you don't have to do equilibrium anymore. So you're trying to calculate the suspended mass required. So whatever the suspended mass is, it's the same as that tension force. The weight of it is the same as the tension force. So if we calculate the weight and divide by 9.81, we've got the mass. Okay, so this tension force is the same as that weight. So we're going to calculate this tension force. So we can tell that times 0.36 is equal to that times 0.83. So clockwise moments is equal to anti-clockwise moments. And the clockwise moments is the tension force. So it's tension times, and it's 0.83. And that's equal to 15 by 9.81 is the weight of the leg, and its distance is 0.36 metres from the pivot. And when you do that calculation, the tension force comes out to be 63.8 newtons. But we need the mass that's causing that tension force, so that is the same as the weight of the mass, and therefore the mass is equal to 63.8 divided by 9.81. And that comes out to be 6.503 kilograms. And we'll just leave it to two significant figures, 6.5. To satisfy the equilibrium condition in B, so that's an equilibrium condition that all the forces are equal. Another force acts on the leg at the hip joint. State the magnitude and direction of this force. So if I just draw that in, that upward force, and we'll call it reaction force just, that tension and reaction force must be equal to the 15 by 9.81. So you know that T which was 63.8, plus that reaction force is equal to the 15 times 9.81. And therefore that reaction force comes out to be 83.4 newtons. And its direction is up.